Hello everyone. Welcome to today's tutorial on how artificial intelligence is transforming the landscape of drug discovery. In this video, we'll explore the essential concepts, methodologies, and practical coding examples related to using AI in this critical field. Before we dive into coding, let's understand what drug discovery entails. It's a complex, time-consuming process that involves identifying new medications. Traditional methods can take years, but with the power of AI, we can accelerate this process significantly. We'll be looking into using machine learning, specifically deep learning techniques, for predicting how different compounds will interact with biological targets. Let's start with the basics of what AI can do in drug discovery. AI can help in various stages such as target identification, lead compound discovery, and in silico trials. The first programming example I'll show you leverages publicly available data to build a predictive model using Python and several machine learning libraries. For our example, we will use a dataset from the ChEMBL database, which contains bioactivity data for different compounds. Make sure you have the necessary libraries installed. The main libraries we will be using are NumPy, Pandas, and scikit-learn. Once we've installed the libraries, we'll start by loading our dataset and exploring it. Here is a basic example of how we can do that. This code reads a CSV file containing our biological activity data and prints the first 5 rows. It's essential to understand your data before modeling. Look at the features available. Typically, you will have columns representing features of the compounds and a target variable indicating bioactivity. Next, we need to pre-process our data. Cleaning and preparing the data is crucial, as any inconsistency can lead to inaccurate predictions. Here's an example of how to handle missing values and encode categorical variables. In this segment, we're filling missing values with the mean of the respective columns and encoding our target variable, activity. Next, we need to split our dataset into training and testing sets to evaluate our model's performance accurately. Now that we have our training and testing datasets, it's time to choose a machine learning model. A popular choice for classification tasks is the random forest classifier. Let's implement it. With our model trained, it's crucial to evaluate its performance on the test set. We can use various metrics such as accuracy, precision, recall, and the F1 score. Let's implement this next. This code will give us an overview of how well our model performs. Remember, achieving high accuracy is important, but we also want to ensure that our model can generalize, especially in a field as sensitive as drug discovery. Now, let's pivot to another approach, using neural networks for predicting drug interactions. For this purpose, we will use the Keras library with a TensorFlow backend. First, ensure you have these libraries installed. Next, we will define our neural network architecture. Here's a straightforward example of how to create a neural network for classification. In this model, we start with an input layer followed by 2 hidden layers. The activation function relu allows for nonlinear transformations, while the final layer uses sigmoid for binary classification. Next, we compile our model and fit it to the data. Compiling the model sets the loss function and optimizer. We opted for binary underscore cross entropy because our outputs are binary. Adjusting the number of epochs and batch size will affect our training duration. After training, we'll evaluate our model. You'll notice neural networks can sometimes outperform classical methods like random forests, especially as the dataset scales. However, they also require more data and computational resources. Keep this balance in mind as you move forward with your projects. Now let's discuss a crucial aspect of AI, interpretability. Understanding how your model arrives at its predictions is essential in healthcare and pharmaceuticals. Techniques such as SHAP values or LIME can help shed light on which features influence your model's predictions. In this example, we introduced SHAP, Shapley additive explanations, to visualize which features are most impactful. This understanding is vital, especially in drug discovery, where regulatory guidelines require comprehensible algorithms. Moving beyond prediction, AI can also assist in generating novel chemical compounds. This process, known as generative modeling, can create new molecular structures. Tools such as GANs, generative adversarial networks, or variational autoencoders can be excellent choices here. In this code stub for a GAN, we define the generator model. This generator can take random input and produce new compounds, which can be evaluated for their potential bioactivity using our earlier models. While we could dive deep into generative modeling, our time here is limited. I encourage you to explore these concepts further as they hold immense potential for drug discovery. However, it's also essential to remain cautious when generating compounds, as not all generated structures will have desired properties. To wrap up, we have covered several key applications of AI in drug discovery, from predictive modeling to generative modeling. We've worked with data, implemented machine learning algorithms, and discussed model interpretability and generative approaches. Thank you for watching. I hope you find these techniques beneficial for your projects. Remember to like and subscribe for more tutorials on programming and AI applications in various fields. If you have any questions or comments, feel free to leave them down below.